The cosmos has a final, silent chapter written into its most fundamental laws. This is the heat death of the universe, a distant but inevitable future where all activity ceases in a state of perfect, frozen equilibrium. By the end of this journey, you will have a clear understanding of this profound scientific prediction and how it reshapes what we think about time, existence, and our own place within the grand story of everything. We will trace the universe's path from the vibrant stellar era we know today to an era of deep cold and stillness, exploring mysteries like the true nature of the dark energy pulling the cosmos apart and whether even black holes, those seemingly eternal prisons, eventually fade from existence. What does the idea of an ending so absolute make you feel about the time we have now? This final stillness is not a random event, but the ultimate consequence of a law that governs everything from a cooling cup of coffee to the lifespan of stars. It is the second law of thermodynamics, a principle so profound it describes the one-way direction of time itself. At its heart is a concept called entropy, which we can think of as a measure of disorder or randomness in a system. The law states that in any isolated system, one left entirely to its own devices, entropy always increases, it never decreases. Imagine a meticulously wound clock, its springs tight and gears perfectly aligned, ready to tick for days. If you leave it alone, it will slowly unwind. The ordered energy stored in the spring will dissipate as sound and a tiny amount of heat, spreading out into the room until the mechanism is still. You will never walk into a room and find a stopped clock has wound itself back up. That spontaneous return to order is forbidden by this fundamental rule. The universe, in the grandest sense, is that isolated system. Every process within it, every star burning, every planet orbiting, every life form thinking, is part of a great and irreversible scattering, a dispersal of concentrated energy into a more uniform, more disordered state. This relentless march toward maximum entropy is what physicists mean by the arrow of time. It gives our lives and our history a direction from past to future, from order to disorder. In the 19th century, thinkers like Lord Kelvin and Rudolf Clausius first grasped the chilling implications of applying this law to the cosmos. They realized that if the universe was finite and obeying these rules, it was inevitably progressing toward a state of thermodynamic equilibrium, a final, uniform temperature where no energy differences exist anywhere. In such a state, no work can be done, no structures can form, and no processes can occur. It is the ultimate stillness, the heat death. What began as a philosophical speculation grounded in the new science of heat engines has, over a century and a half, become a cornerstone prediction of our standard model of cosmology. The discovery of the universe's expansion and the cosmic microwave background radiation provided the framework. We now see the cosmos as a starting point of incredibly high density and temperature, the Big Bang, and this law tells us its most probable end point, an expanse of profound cold and silence. This sets the stage for our journey, a timeline from the vibrant era we inhabit to that distant, quiet finale. Our universe's story is a grand epic written across unimaginable spans of time, and we find ourselves in a remarkably vibrant early chapter. This entire narrative, from the first flash of existence to the final whisper of darkness, can be understood as a journey through distinct eras, each defined by the dominant sources of light and energy. We live in what cosmologists call the Stelliferous Era, the age of stars. It began with the first stars igniting a few 100 million years after the Big Bang, and it will continue for trillions more. Right now, the cosmos is a brilliant tapestry of galaxies, with new stars being born from great clouds of gas and dust, shining for millions or billions of years, and then dying in spectacular supernova that seed the cosmos with the elements for planets and life. It feels eternal, but it is only a phase. Gravity, the great architect, is slowly but surely using up the available fuel. Over eons, galaxies will drift apart as the universe expands. Star formation will sputter and cease as gas is locked away in dead stars, and the lights will begin to go out one by one. This marks the transition into the Degenerate Era, a time stretching for quadrillions of years. The universe will be a much darker place, illuminated only by the faint, residual glow of stellar corpses, white dwarfs and neutron stars slowly cooling like embers in a cosmic fireplace. Black holes will wander this vast graveyard, growing occasionally by swallowing the sparse, cold matter that remains. Eventually, even those cooling embers will fade to black, and the universe will enter the black hole era. For a time incomprehensibly longer than the previous ages, these gravitational titans will be the last organized structures, slowly losing mass through a faint quantum process called Hawking radiation. One by one, over timelines that dwarf all of human history, they too will evaporate in a final, silent puff of particles. What remains is the final epoch, the Dark Era. A universe of unimaginable scale, filled with only the most fundamental particles and radiation, stretched so thin and so cold that no two particles may ever meet again. To grasp the scale of this timeline, try this. If we compress the entire lifespan of the universe, from the Big Bang to the last evaporating black hole, into a single 24-hour day, our entire Stelliferous Era, with all its galaxies and stars and civilizations, would be over in the first fraction of a second after midnight. Everything we know, every story ever told, every triumph and tragedy fits into that blink of cosmic time. The remaining 23 hours, 59 minutes, and 59.999 seconds are the long, slow fade to black. This is not a story of sudden catastrophe, but of a gradual, inevitable winding down, a universe patiently exhausting every possible source of concentrated energy, step by step, toward that state of perfect equilibrium. The direction of time feels like the most obvious fact of our existence. We remember yesterday, but we have no memory of tomorrow. A shattered glass stays shattered. It never leaps back onto the table fully formed. This one-way flow from past to future is so ingrained in our reality that we rarely pause to ask why it exists at all. What physical law makes the past different from the future? The answer lies not in the fundamental particles themselves, but in the arrangement of those particles, in a concept we touched on earlier, entropy. Entropy is often described as disorder, but a more precise way to think of it is as the number of possible arrangements a system can have while still looking the same from the outside. A tidy room has low entropy. There is only one or two ways for everything to be perfectly in place. A messy room has high entropy because the clothes on the floor and the books on the bed can be in a near infinite number of positions, and the room still looks, well, messy. The universe follows a simple but profound rule. It tends to move from states of lower entropy, fewer arrangements, to states of higher entropy, more arrangements. This is the second law of thermodynamics. An egg can easily scramble because there are countless ways for the yolk and white to be mixed together. For that mixture to spontaneously unscramble and reform a perfect yolk inside an unbroken shell, however, would require hitting upon the one exact arrangement out of trillions. It is not impossible, just staggeringly, cosmically unlikely. This relentless statistical drift toward higher entropy is what physicists call the arrow of time. It is the reason we experience cause and effect, and why history has a coherent narrative, but this raises a profound mystery. If the universe is always moving toward higher entropy, then it must have started in a state of incredibly low entropy. And indeed, our best model of cosmic origins, the Big Bang, describes exactly that, a moment of extraordinarily high density and temperature, but also of exquisite simplicity and order. From that singular starting point, the universe has been unfolding and dispersing ever since, like a wound-up clock slowly unwinding. The great physicist Ludwig Boltzmann once pondered a strange implication of this statistical view. Given enough time, random fluctuations in a high-entropy universe could, by sheer chance, create a pocket of low entropy. In principle, a fully formed, conscious brain could even fluctuate into existence out of the chaos, complete with false memories of a past that never was, a so-called Boltzmann brain. The fact that we are not such fleeting fluctuations but part of a vast, coherent, low-entropy past tells us something crucial about our universe's initial conditions. It began in a very special, very ordered state, setting the arrow of time flying. Could time flow backward in a different cosmos? If such a universe started in a state of maximum entropy, there would be no arrow, no past or future as we understand it, just eternal, static equilibrium. Our experience of time, of memory and anticipation, of broken glasses and aging stars, is a gift of that improbable beginning, a single direction carved out of randomness, guiding everything, including the cosmos itself, toward its final, quiet rest. The arrow of time points toward stillness, but the clock of the cosmos is not just winding down, it is being actively pulled apart. In the late 1990s, astronomers made a discovery that reshaped our entire cosmic forecast. They were measuring the distances to extremely far-off supernovae, expecting to confirm that the universe's expansion was gradually slowing down due to the collective gravity of all matter. Instead, they found the opposite. The most distant stellar explosions were fainter than predicted, meaning they were farther away than anyone had calculated. The expansion of the universe was not slowing, it was accelerating. Something was acting against gravity, pushing galaxies apart at ever-increasing speeds. This mysterious something earned the name dark energy. Think of it as a kind of anti-gravity, a repulsive force woven into the fabric of space itself. As the universe expands, more space is created, and with it, more of this repulsive energy. It is a runaway process. To visualize this, imagine drawing dots on the surface of a balloon, then inflating it faster and faster. The dots, representing galaxies, do not just move apart, they accelerate away from each other, carried by the stretching fabric. In our real universe, this relentless acceleration has a profound consequence for the heat-death scenario. It does not just spread matter out, it dilutes it. Galaxies that are gravitationally bound today, like our own Milky Way and its neighbors, will stay together, but every other galaxy cluster will eventually be pushed beyond our cosmic horizon. The observable universe will shrink to our local group, and then, over eons, even the stars within our own galaxy will become isolated points of light in an ever-darkening void. Dark energy ensures that the final state is not just cold but profoundly lonely, making the journey to maximum entropy faster and more absolute. What is this strange force? The leading idea is that it is a property of empty space itself, a cosmological constant, as Einstein once proposed for a different reason. Its strength would remain steady, leading to the accelerated expansion we see. Other theories suggest dark energy could be a dynamic field that changes over time, perhaps even weakening or strengthening in ways that could alter the ultimate fate. This is one of the greatest unknowns in all of science. The nature of dark energy dictates the timeline and the character of our universe's final chapters. Without it, gravity might have eventually pulled everything back together in a big crunch, a fiery reversal of the Big Bang. With it, the story is one of endless expansion and dispersal, a quiet fade instead of a dramatic collapse. This mystery sits at the very heart of cosmology, a silent force guiding everything toward an end we are only beginning to comprehend. The brilliant stars we see tonight are not just points of light, They are the universe's great alchemists, transforming the simplest element into the ingredients for everything we know. Deep within their cores, under immense pressure and heat, stars perform nuclear fusion, the process of squeezing atomic nuclei together. It begins with hydrogen, the most abundant element, fusing into helium. This reaction releases the energy that makes a star shine. For a star like our Sun, this stable phase will last for about 10 billion years. But when the hydrogen fuel in its core is exhausted, the star evolves. A Sun-like star will swell into a red giant, eventually shedding its outer layers in a beautiful planetary nebula, while its core collapses into an incredibly dense Earth-sized object called a white dwarf. This white dwarf, initially white-hot, has no internal furnace left. It is a dying ember, radiating its residual heat into the cold of space. Over trillions upon trillions of years, it will slowly, imperceptibly cool, fading from white to red to infrared, and finally to invisible blackness, becoming a cold, dark crystal of carbon and oxygen known as a black dwarf. Our Sun will one day become such a silent, dark cinder, a monument to a fire that once warmed a planetary system. More massive stars live faster and die more violently. They fuse elements far beyond helium, creating carbon, oxygen, neon, and silicon in successive shells, like layers of an onion, until their core is iron. Iron is different. Fusing iron does not release energy, it consumes it. When an iron core grows too large, the star's support vanishes in an instant. The core catastrophically collapses, then rebounds in a titanic explosion called a supernova. This violent blast, for a brief moment, creates elements heavier than iron, like gold, silver, and uranium, and flings all these newly forged elements into the interstellar void. The remnant left behind is either an ultra-dense neutron star, a city-sized object where a teaspoon of material would weigh 1 billion tons, or, for the most massive cores, a black hole. These stellar corpses become the dominant actors in the next cosmic eras, yet even they are not permanent. Over timescales that make the age of the universe seem like a blink, theoretical physics suggests that matter itself may not be eternal. The protons and neutrons that form atomic nuclei are thought to be stable, but some grand unified theories predict a process called proton decay. If true, over a period perhaps 1 million trillion times the current age of the universe, the protons in every atom of every dead star and frozen planet would spontaneously disintegrate. A proton would decay into lighter particles like positrons and photons, and the very building blocks of matter would dissolve away. This would leave behind only a sea of leptons like electrons and radiation drifting in the vast dark. This entire journey, from shining star to cold black dwarf, from supernova-forged iron to the theoretical decay of a proton, is a powerful illustration of entropy's relentless increase. The universe begins with light, simple elements like hydrogen in a highly ordered, low-entropy state. Stars act as temporary islands of order, concentrating this fuel to create heavier, more complex elements. But in doing so, they radiate enormous amounts of energy out into the cold void, energy that is scattered and can never be fully gathered again. The beautiful structures, the planets, and the people they make possible are fleeting eddies in this great flow toward dispersion. When the last star dies and the last proton decays, all that beautiful complexity, all the intricate order forged in stellar furnaces, will have been returned to the most uniform, disordered state possible, a thin, cold haze of fundamental particles. The story of matter is the story of the universe slowly forgetting how to be anything but simple and still. Even black holes are not truly eternal. They stand as the final, formidable structures in a darkening cosmos, colossal anchors of gravity that seem to defy the universe's drift toward disorder. For eons beyond count, they will dominate the black hole era, the sole remaining landmarks in an expanse of fading radiation and subatomic particles. Yet a profound discovery by Stephen Hawking revealed that these gravitational titans are not perfect prisons. Through a subtle quantum effect at the very edge of their boundaries, black holes slowly leak energy. This process, Hawking radiation, causes them to lose mass, shrinking over time until they ultimately evaporate. The timescales involved are almost beyond human comprehension. A stellar mass black hole formed from a collapsed star might take 10 to the power of 67 years to vanish. That is a 1 followed by 67 zeros. A supermassive black hole, like the one at the heart of our Milky Way, could persist for 10 to the power of 100 years, a number so vast it dwarfs every other timescale we have discussed. Their evaporation would be among the very last organized events in the entire cosmos, a final, faint flicker of process before the long dark era truly begins. This leads to one of the most fascinating puzzles in theoretical physics, the black hole information paradox. Quantum mechanics, the rules governing the subatomic world, states that information is never truly destroyed. The specific arrangement of particles that falls into a black hole, in principle, should be preserved in some form. But if a black hole evaporates completely through Hawking radiation, which appears to be random thermal noise, where does that detailed information go? Does it vanish forever, violating a cornerstone of physics, or is it somehow encoded, scrambled into the radiation itself? This paradox suggests our understanding of gravity and quantum mechanics is incomplete at this extreme frontier. Theorists like Leonard Susskind have proposed revolutionary ideas to resolve it, such as the holographic principle. This concept suggests that all the information describing everything within a three-dimensional volume of space, like the interior of a black hole, can be perfectly encoded on its two-dimensional boundary, its event horizon. It is as if the entire content of a room, every object and detail, could be described entirely by the patterns on its walls. If true, when a black hole evaporates, the information is not lost, but slowly and chaotically released back into the universe through its radiation. So what does the end of a black hole look like? As it shrinks, its temperature rises, and the rate of evaporation accelerates. The final moments could involve a burst of energy, a last gasp of particles and radiation. However, for the largest black holes, this process is so drawn out and the final output so diffuse across cosmic time that it might not be a dramatic explosion, but more of a quiet final sigh. Whether a pop or a fizzle, this event marks a profound transition. It signifies the end of the last objects that could meaningfully curve space-time, the last entities that could be said to have a distinct location and history. After the last black hole vanishes, the universe enters its final, purest state, a realm where the very concepts of here and there, before and after, begin to lose their meaning. The stage is now set for that ultimate equilibrium, a cosmos of profound simplicity and silence. The universe's final state is not one of empty blackness, but of a thin, cold sea of energy stretched to its absolute limit. This is the ultimate destination of all light, all radiation ever produced. Every photon, every particle of light emitted by a star, a galaxy, or even the fading glow of the last black hole, is on an endless journey through expanding space. As space itself stretches, it stretches the light traveling through it, lengthening its wavelength in a process called cosmological redshift. Think of drawing a wave on a rubber band, then slowly pulling the ends apart. The wave crests become farther apart, its energy diluted. A photon that began as visible starlight is redshifted to infrared, then to microwave, then to radio waves, its energy dwindling with each passing eon. Even the cosmic microwave background radiation, the faint afterglow of the Big Bang itself, is not immune. Today it is a chilly -270 degrees Celsius, just a few degrees above absolute zero. Over hundreds of billions of years, it too will be redshifted into oblivion, its temperature asymptotically approaching that impossible cold floor, absolute zero. This is the great dilution where the energy of the cosmos is not destroyed but rendered unusable, spread so evenly that no work can be extracted from it. It is the difference between a roaring waterfall that can turn a mill wheel and a placid, continent-wide lake where the water is perfectly level. Both contain water, but only one has the difference in height, the gradient, that allows for motion and change. The heat-death universe is that vast, still lake but made of light and particles. Within this cold sea, the remnants of matter face a profound loneliness. Stable particles like electrons and positrons, if they survive proton decay, will be so impossibly far apart that the chance of any two meeting becomes essentially zero. The average distance between particles could grow to be larger than our entire observable universe is today. For a hypothetical observer, the sky would be utterly black with no stars or galaxies, and the ambient temperature would be indistinguishable from absolute zero. There would be no here or there that is warmer or colder, no energy gradients whatsoever. The entire cosmos reaches a perfect, uniform equilibrium. You can see a miniature version of this process on your own kitchen counter. A hot cup of coffee does not explode, it simply sits and cools. The concentrated heat energy within it disperses into the air of the room, moving from a state of high temperature to a state of equilibrium with its surroundings. Once the coffee and the air are the same temperature, the process stops. No further energy can be extracted from that system. The universe is undergoing this same process, but the cup is all of space, and there is no outside room for the heat to go into. It simply spreads within the cup forever, becoming colder and more dilute with each passing moment. This is the quiet truth of the heat death, a deep freeze so complete that the concepts of time and change may themselves lose all meaning. But even a cosmos in perfect equilibrium may not be completely dead. There is a fourth mystery, a whisper of possibility from the quantum realm. According to quantum mechanics, the vacuum of space is not truly empty. It is a seething sea of potential, where pairs of particles and their antiparticles can spontaneously flicker into existence for the briefest of moments before annihilating each other. In a universe stretched to maximum entropy, these quantum fluctuations would be the only remaining events. And given enough time, an amount of time that makes our current cosmic age seem like a single heartbeat, even the most improbable of these fluctuations could, in theory, occur. This leads to one of the most mind-bending ideas in all of cosmology, the concept of a Boltzmann brain. Named for the physicist who first pondered these statistical oddities, a Boltzmann brain is not a biological organ. It is a hypothetical, fully formed, self-aware entity that could spontaneously assemble from a random quantum fluctuation in the cold, dark void. It would appear complete with fabricated memories and sensory inputs, experiencing what it believes to be a real, coherent universe for only an instant before dissolving back into the chaos. The probability of such an event is so vanishingly small that it is essentially zero for all practical purposes. Yet, over a literally infinite span of time, the impossible becomes inevitable. So, does this mean a dead universe could eventually restart itself? Could a fluctuation create not just a single brain, but an entire new cosmos, a big bang from randomness? The mathematics suggests that a fluctuation producing an entire low-entropy universe like our own is actually more probable than one producing a single, isolated brain, because there are more ways to arrange the particles for a vast cosmos than for one specific, complex object. This is a profound and unsettling idea. It implies that in an eternal, high-entropy sea, pockets of order like our universe might bubble up occasionally like foam on a vast, still ocean. Our entire cosmic history, from the first star to you listening right now, could, in principle, be one such rare but statistically inevitable fluctuation. This presents a serious puzzle for cosmologists. If we are more likely to be Boltzmann brains hallucinating a universe than beings in a real, coherent cosmos that began with a low-entropy Big Bang, then our scientific observations are an incredible illusion. Most physicists reject this conclusion, not because it is impossible, but because it makes science itself untrustworthy. They argue that the fact we perceive a consistent, law-governed universe with a clear past and shared reality is strong evidence that we are not such fleeting phantoms. The debate forces us to the very edge of physics and philosophy. It asks what we mean by reality itself. If a Boltzmann brain did flicker into being, what would it experience in that instant? Would it perceive a universe or just a chaotic flash of sensation? And more importantly, what does our own sustained, ordered existence tell us about the true nature of our cosmos? It suggests that our universe's beginning was not a random accident, but something special, a boundary condition that set a reliable arrow of time, allowing for the long, intricate story we find ourselves within. These timelines stretch so far beyond our daily experience that our minds simply cannot hold them. To even begin to grasp the scale, we must shrink the cosmos down to a human measure. Let us compress the entire current age of the universe, all 13.8 billion years from the Big Bang to today, into a single calendar year. In this cosmic year, the Big Bang happens at the stroke of midnight on January 1st. Our solar system forms around September 2nd. Dinosaurs roam the Earth in late December, and all of recorded human history, from the first cities to this very moment, unfolds in the last 10 seconds before midnight on December 31st. Now, where on this scale does the heat death occur? It is not in the next year or the next century. The processes we have described, the fading of the last stars and the evaporation of the final black holes, would begin many, many cosmic years from now. We are talking about timelines so vast that if our one cosmic year represented all of human civilization, the wait for the last black hole to vanish would be longer than all of human history repeated over and over again for centuries. Scientists use powers of 10 to describe these spans. A googol is 10 to the power of 100, a 1 followed by 100 zeros. The estimated time for the largest supermassive black holes to evaporate is roughly a googol years. To write that number out in full would take more pages than all the books in the largest library, and each zero represents a factor of 10 longer than the last. In his book, The 5 Ages of the Universe, astronomer Fred Adams describes these far future epochs as operating on what he calls poetic timescales. An event that happens once every 10 to the power of 50 years is, for all practical purposes, never happening at all from the perspective of any conceivable observer. The universe enters a state that is effectively static, a frozen tableau where the interval between any two meaningful events is longer than the previous age of the cosmos itself. What does this immense depth of time do to our sense of place and purpose? It can feel dwarfing, certainly. All of our struggles, our art, our love, and our wars are contained within that fleeting 10-second sparkle at the end of the cosmic year. Yet, this perspective is also strangely liberating. It means that our era, the Stelliferous Era, is not some mundane average state of the cosmos, but a brilliant, fleeting fireworks display. We exist in the cosmic springtime, a brief window of light and structure between the primordial fire and the long winter night. The heat death is the inevitable resting state, but our story is written in the extraordinary departure from that equilibrium. Our legacy is not etched in stone for eternity, because eternity, in this cold thermodynamic sense, is a very quiet place. Instead, our meaning is woven into the temporary, vibrant order of this moment, a spark of consciousness flickering in the brief age of stars. This realization invites a quiet reflection. What we do with our time matters not because it will echo forever in a silent universe, but precisely because it will not. The transience is what gives it weight. But is this frozen, silent finale truly the only possible ending for our story? While the heat-death scenario is the most widely accepted forecast based on everything we currently know, the cosmos has a way of surprising us. Our scientific models are powerful, but they are built on our present understanding of forces like dark energy and gravity, and those understandings could evolve. Several alternative cosmic fates have been proposed, each painting a very different picture of the final moments. The first is known as the Big Rip. Imagine dark energy is not a constant force but grows stronger over time. Instead of simply pushing galaxies apart, it would eventually overpower every force that holds things together. First, galactic clusters would be torn asunder, then individual galaxies. As the repulsion intensifies, it would rip stars from their solar systems and planets from their stars. In the final, terrifying moments, even atoms and atomic nuclei would be shredded apart by the stretching fabric of space itself. The universe would end not with a whimper, but with a violent, instantaneous disintegration of all structure. This is the ultimate victory of expansion over cohesion. A second, contrasting possibility is the Big Crunch. This is the classic mirror image of the Big Bang. If the density of matter and energy in the universe were high enough, gravity could eventually overcome the outward push of dark energy. The expansion would slow, halt, and then reverse. Galaxies would begin rushing back toward each other, space itself would contract, and temperatures and densities would soar. The cosmos would collapse back into a singularity, a state of infinite density, potentially triggering a new Big Bang. This cyclical idea leads directly to a third scenario, the Big Bounce. In this model, the universe undergoes an endless series of expansions and contractions, a cosmic heartbeat lasting perhaps trillions of years. Each cycle begins with a Big Bang and ends with a Big Crunch, which then reboots into a new expansion. Crucially, some versions of this theory suggest that with each bounce, the universe is reset in a sense, with entropy perhaps being smoothed out or reconfigured, avoiding a permanent heat death. How do these dramatic alternatives compare to our quiet heat death forecast? The key difference lies in the ultimate state of entropy. The heat death represents maximum entropy, a uniform, timeless equilibrium. The Big Rip is also a high entropy end, but one achieved through catastrophic disintegration rather than slow dilution. The Big Crunch and Big Bounce, however, are more mysterious. A classic crunch that ends in a singularity seems to erase information and reset entropy to zero, which poses deep thermodynamic puzzles. A successful bounce would require a mechanism to reset or circumvent the entropy increase of the previous cycle, something our current physics cannot fully explain. These are not just wild speculations, they are serious scientific hypotheses that hinge on unanswered questions. The true nature of dark energy is the biggest wild card. Is it truly constant, or does it evolve? The answer dictates whether we get a gentle expansion leading to heat death or a violent Big Rip. Similarly, a theory of quantum gravity, which would unite Einstein's relativity with quantum mechanics, might reveal new physics at the moment of a crunch or a bounce, showing how the universe could transition from one cycle to the next. Our cosmic forecast, therefore, remains provisional. It is the best story we can tell with the evidence on hand, but future discoveries from next-generation telescopes or breakthroughs in theoretical physics could dramatically rewrite the final chapter. This uncertainty is not a weakness of science, but its greatest strength, a reminder that the universe is still a book with many pages left to read. This ultimate stillness presents a profound philosophical puzzle, one that physicists call the black hole information paradox. The conflict is stark. On one side, thermodynamics and general relativity, the rules governing gravity and large scales, suggest that when matter falls into a black hole, all the specific information about that matter, the precise arrangement of its particles, is lost forever, trapped behind an event horizon that eventually evaporates away. The black hole radiates only generic heat, a thermal whisper that carries no details. On the other side, quantum mechanics, the rules of the very small, insists that information can never be truly destroyed. It must be preserved, scrambled perhaps, but always in principle recoverable. So, what happens? Does the universe forget? This is not just an abstract debate about black holes. It is a direct challenge to our understanding of reality itself, and it has deep implications for the heat-death scenario. Stephen Hawking famously argued for a long time that information was indeed lost in black holes, a conclusion that troubled many of his colleagues, including Leonard Susskind, because it would mean the fundamental laws of quantum physics break down under extreme gravity. Gerard T. Hooft, another giant in the field, took the opposite view. He championed the idea that information must be preserved, suggesting that the solution lay in rethinking how we view space. This led to a revolutionary concept, the holographic principle. It proposes that all the information contained within a volume of space can be perfectly described by data encoded on its two-dimensional boundary, like a three-dimensional movie being projected from a flat screen. For a black hole, that screen is its event horizon. In this view, the information of everything that falls in is not lost inside, but is smeared and stored on this spherical surface. When the black hole evaporates via Hawking radiation, that information is slowly and chaotically released back into the universe. Now, connect this to the heat death. If information is preserved, even in the cold, dilute haze of the final dark era, then in some highly scrambled, inaccessible form, the entire history of the universe, every star that shone and every thought that was ever had, is still encoded in the quantum state of that vast, cold vacuum. The cosmos would not suffer true amnesia. Its story would be frozen into the ultimate, low-energy pattern of its fields and particles, a cosmic fossil of unimaginable complexity. But if information can be lost, if the Hawking of the paradox is correct, then the heat death is more than just an end of activity. It is an erasure. The universe's memory of its own spectacular beginning and vibrant middle age is gradually deleted as black holes evaporate and particles drift apart. The final state would be one of maximum entropy, not just in energy, but in information, a state of complete forgetfulness. What does this mean for the arrow of time we discussed earlier? Our experience of past and future relies on a universe that remembers, where causes leave effects that can be traced. If information is preserved, even at heat death, that arrow has a logical, if frozen, endpoint. The history is still there, just locked in place. If information is lost, the very foundation of causality becomes fuzzy. The universe's story would have missing chapters that can never be recovered, suggesting that at the most fundamental level, time itself might not be the reliable, one-way flow we perceive. This paradox forces us to ask, is the cosmos ultimately a system that conserves its story, or one that forgets it? The answer lies in a theory we do not yet have, a complete marriage of quantum mechanics and gravity. Until we find it, the final moments of time hold not just the mystery of silence, but the deeper mystery of whether anything, in the end, truly mattered. The universe's final eons seem devoid of any possibility for thought, but some minds have dared to sketch a different picture. Could life, or some form of consciousness, find a way to persist even as the cosmos winds down? This is not about biology as we know it, but about the fundamental need for information processing, for a system to gather, store, and use energy to maintain complexity against the tide of entropy. In the far future, the energy sources we rely on will be gone. Yet, theoretical physicist Freeman Dyson once pondered whether an intelligent civilization could adapt. He framed the challenge in terms of open and closed boxes. An open box can exchange heat with its surroundings, but in a universe nearing uniform temperature, there is no cooler outside to dump waste heat into. A closed box, like the universe itself, has no external reservoir. Within such a system, the ability to do work, to think and compute, depends entirely on exploiting the tiny, fading temperature differences that might still exist. Dyson speculated that life could slow its metabolic rate to match the cooling cosmos, performing fewer and fewer thoughts per eon, but perhaps never stopping entirely, stretching a finite store of consciousness across an infinite timeline. Later calculations suggested more severe limits, but the poetic idea remains compelling, a vision of mind becoming a deep, slow meditation in the dark. Others have looked to the last great energy sources, black holes. A civilization of the distant future might learn to extract energy from a black hole's rotation, a process known as the Penrose process, or even from the Hawking radiation of smaller ones. They could build immense, fragile structures, Dyson spheres not around stars, but around these gravitational engines, eking out a dwindling existence. Their reality might be entirely virtual, a vast, slow computer simulation running on the last trickle of power, where 1 billion years of subjective experience passes in the real universe's last second. The science fiction writer Olaf Stapledon, in his novel Star Maker, envisioned minds merging across galaxies in the final days, sharing a collective consciousness that contemplates the cosmos itself. These are stories, of course, thought experiments that push physics to its limits. They lead to a haunting philosophical question. If a form of consciousness could last indefinitely, slowing its thoughts to match the cooling of space, what would it experience as time itself approaches its end? Would it perceive the final proton decays, the last evaporating black holes, as events within its awareness? Or would its perception become so dilated that the death of the universe would be a single, frozen, eternal moment, a final thought that never concludes? This blends science with deep existential reflection. What, then, would be the purpose of existence in a cosmos that is nearly dead? If the goal is survival, then persisting in such a state is a kind of triumph, a declaration that consciousness is the universe's way of knowing itself, even in its final hours. But if the goal is meaning derived from action, creation, and connection, then a near-infinite, near-static existence might feel like the opposite of life. It asks us what we truly value about being aware. Is it the mere fact of perception, or is it the dance of change, of growth and loss, that happens only in a universe with a clear arrow of time and gradients of energy? Our vibrant stellar era provides those gradients in abundance. We live in the brief cosmic spring where change is possible, where stories can be told. That may be the most precious condition of all. The last chapter of the cosmos is written in the language of fading temperatures and vanishing gradients. As the heat-death scenario approaches its conclusion, the ambient temperature of the universe does not simply drop to a certain point and stop. Instead, it asymptotically approaches absolute zero, the theoretical temperature where all molecular motion ceases. It gets closer and closer, like a curve on a graph that forever nears a line it can never touch. This march toward the ultimate cold is driven by the relentless expansion of space, stretching the wavelength of every last photon into oblivion. Yet, even at this theoretical limit, the universe is not completely dead in the classical sense. Quantum mechanics introduces a faint, irreducible hum. This is the zero-point energy, a fundamental jitter of the vacuum itself, a minimum energy that can never be extracted or used to perform work. It is the universe's baseline, a quiet static at the bottom of everything. Within this cold sea, the last structures of matter face their own endings. If the grand unified theories are correct, the very protons and neutrons that form atomic nuclei are not truly stable. Over a timescale of perhaps 10 to the power of 34 years or more, a process called proton decay could occur. A proton, one of the building blocks of every atom in your body and in every star, might spontaneously transform, decaying into lighter particles like a positron and pions, which then decay further into photons. This would be the ultimate dissolution of matter as we know it. For any remaining electrons, a strange final partnership might form. An electron and its antimatter counterpart, a positron, could become gravitationally bound into an exotic atom called positronium. This fragile structure would orbit for an unimaginably long time before the two particles finally spiral together and annihilate in a final flash of gamma rays, a last spark in the dark that might be the final recognizable atomic event in all of existence. The timeline of these last events is a narrative of deepening silence. Long before proton decay becomes significant, the last organized events will be the evaporation of the largest black holes. After googles of years, even the supermassive giants at the hearts of galaxies will have shed their mass through Hawking radiation. Their final moments are not a cataclysm, but a quiet dissolution. As a black hole shrinks, its temperature rises, and the rate of evaporation accelerates. The last stages might produce a faint, final burst of particles and radiation, a last whisper of information being returned to the cosmos. Picture the last ember in a vast, cold fireplace, glowing faintly for a moment before its light winks out, leaving only a uniform, ambient darkness. That final puff from the last black hole marks a profound transition. It is the end of the last objects that significantly warp the fabric of spacetime, the last landmarks in a now featureless expanse. After this, the universe enters its pure dark era. The remaining particles, whether stable electrons or the products of proton decay, are so unimaginably far apart that they are effectively isolated forever. The concept of an event loses all meaning, as the time between any two particles interacting could be longer than the previous age of the universe. The cosmos becomes a static, ultra-low-energy quantum field, a perfect equilibrium where the arrow of time itself may cease to have any discernible direction. This is the ultimate expression of entropy's victory, a state of such perfect uniformity that nothing can ever happen again. The quiet fade of heat death is not the only way our story could end. There is a seventh mystery, one far more abrupt and absolute, that suggests the cosmos might not be allowed to grow old and cold at all. This is the possibility of vacuum decay, a cataclysm born not from the slow exhaustion of energy, but from a fundamental instability in the very fabric of reality. Our understanding of the universe is built upon fields, invisible entities that fill all of space. The Higgs field, for instance, is what gives particles their mass. Current measurements suggest this field might not be in its lowest possible energy state. Instead, our entire cosmos could exist in a metastable false vacuum, like a ball resting in a shallow valley on the side of a much deeper hill. It seems stable for now, but given enough time or the right quantum nudge, it could tunnel through the energy barrier and roll down into the true lowest energy vacuum. This event would not be an explosion in space, but a rewriting of space itself. A tiny bubble of this true vacuum would spontaneously form, perhaps anywhere, and expand in all directions at the speed of light. Its wall would be a boundary where the laws of physics as we know them cease. The fundamental constants, the strengths of forces, the very behavior of matter would be irrevocably altered within the bubble. Any structure, from a galaxy to an atom, would be instantly dismantled and reorganized according to new, unknown rules. Life, consciousness, and information as we conceive them would be impossible. This presents a stark contrast to the distant, inevitable heat death. Vacuum decay is a statistical possibility that could be triggered at any moment, in the next second or in a trillion years. It is a cosmic sword of Damocles, a reminder that the ground beneath our feet, quite literally, might be only temporarily solid. The theoretical framework for this unsettling idea was heavily developed by physicist Sidney Coleman in the 1970s and 80s. His work described the quantum tunneling process and the lethal dynamics of the expanding bubble, painting a picture of an end that offers no warning and allows no escape. This concept has since captured the imagination of popular media, often depicted as an unstoppable wave of annihilation, because at its core, it represents the ultimate existential vulnerability. The chilling questions it raises are profound. Could such an event have already been triggered somewhere in the vastness of the cosmos, with its light-speed wall already on its way? Given the size of the observable universe, it is statistically possible, yet we see no evidence of such a destructive wave. More philosophically, would this erase the possibility of heat death entirely? Absolutely. Vacuum decay would not be an ending within our universe's timeline. It would be the termination of the universe's very rulebook. The long, slow fade to equilibrium would be preempted by a sudden, total transformation into a different kind of reality, one where concepts like stars, protons, and entropy might have no meaning at all. It forces us to confront a humbling truth. The stability we take for granted is not guaranteed by the cosmos, but is a temporary and precious condition of our particular cosmic epoch. The silent fate of the cosmos forces a question far beyond physics. If all structure, all memory, and all life are ultimately transient, what does that mean for our own search for purpose? This is where our scientific forecast collides with ancient philosophical and spiritual inquiry. Many traditions have long grappled with the idea of impermanence. In Buddhist thought, the concept of anicca teaches that all conditioned things are in a constant state of flux and dissolution. Nothing lasts, and attachment to permanence is a source of suffering. The heat-death scenario presents a scientific validation of this impermanence, but on a scale so vast it can feel dwarfing. It challenges the very human desire to build a legacy that echoes through eternity. We etch our names in stone, create art, push for scientific breakthroughs, hoping some part of us will endure. Yet the universe itself seems to be writing a story with a final, blank page. The French philosopher Albert Camus, wrestling with a world devoid of inherent divine meaning, described the human condition as fundamentally absurd. We are beings who crave purpose and significance, thrust into a silent universe that offers none. The heat-death can feel like the ultimate expression of that cosmic silence. So, does this mean our efforts are meaningless? One way to view it is through the metaphor of a sandcastle built with care on a beach. The builder knows the tide will come in. The intricate towers and walls will be smoothed away, leaving no trace. Yet, the act of building was not worthless. The focus, the creativity, the shared joy in that moment held its own intrinsic value. The meaning was in the doing, not in the permanence of the result. Our civilizations, our art, our relationships are like that sandcastle, but built on the shore of cosmic time. Their beauty and significance are not diminished because the tide will one day arrive. They are defined by it. This perspective can be strangely liberating. It shifts the focus from an uncertain forever to the tangible now. If there is no cosmic scoreboard keeping track for eternity, then the value of our experiences, our kindness, our curiosity, and our love is determined entirely by the quality they bring to our brief moment in the light. It invites us to find purpose not in outlasting the universe, but in fully inhabiting our place within its story. Another response to this ephemeral nature is the drive to transcend it. This is the impulse behind concepts like digital immortality or the far future projects of civilizations seeking to harness the last black holes. It is a refusal to accept the tide's verdict, a testament to the enduring will to understand, to adapt, and to persist. Whether such transcendence is possible remains one of our greatest unknowns. The heat-death does not necessarily rob our lives of meaning. It redefines where that meaning can be found. It asks us to consider, in the face of an inevitable end, what matters most to us here in this temporary, brilliant, and fleeting age of stars. A final possibility for the end of everything has nothing to do with physics as we know it, but with the nature of reality itself. This is the eighth mystery, the simulation hypothesis. It asks a startling question: what if our universe, with all its galaxies and laws, is not the base layer of existence, but an incredibly sophisticated computational model, a simulation running on some advanced civilization's hardware? Philosopher Nick Bostrom famously formalized this idea, arguing that if a civilization could ever reach a level of technological maturity capable of running vast, conscious simulations, then it is statistically probable we are living in one of those simulations rather than in the original, biological reality. This speculative idea collides with our forecast of heat death in a fascinating way. If our cosmos is a simulation, then the heat death scenario might not be a law of nature, but a design feature or a system limit. The gradual winding down of usable energy could represent the simulation's processing power being slowly allocated elsewhere, or its memory banks becoming full. The final fade to black could simply be the program reaching its end state, or worse, an administrator deciding to terminate the simulation, hitting the cosmic off switch. This perspective reframes the entire discussion. The physical constants we measure, like the strength of gravity or the mass of an electron, would not be fundamental truths but parameters set by the programmers. The arrow of time and the increase of entropy could be elegant algorithms designed to give the simulation a coherent, forward-moving narrative. In this view, a simulating civilization might even intervene to prevent or alter the end. They could, in principle, reset the parameters, introduce new energy sources, or restart the simulation entirely, turning a heat death into a reboot. This stands in stark contrast to the physical heat death we have explored, which is an inevitable consequence of impersonal, unchanging laws within a self-contained system. One is a technological failure or choice, the other is a thermodynamic certainty. So, how would we ever know? Some thinkers have proposed looking for evidence of optimization or shortcuts in the fabric of reality, like the discrete, pixelated nature of spacetime at the smallest scales, which some theories of quantum gravity already suggest. Others note the surprising fine-tuning of our universe's constants, which seem perfectly calibrated to allow for stars, planets, and life. A simulation architect might set such parameters intentionally. This leads to a profound and oddly modern question. If we are in a simulation, does that make our universe's eventual end more or less meaningful? On one hand, it could feel deeply unsettling, like discovering your entire life and all your loves are part of a game that will one day be closed. The struggle for legacy and understanding would be for naught if the platform itself is temporary. On the other hand, it might introduce a strange kind of hope. An end caused by a shutdown is not an absolute physical inevitability. It is a decision, and decisions can be reconsidered. It also implies the existence of a larger reality beyond our own, a base universe where the simulation is being run, which itself might have very different and perhaps less final rules. This speculation weaves a layer of technological wonder into the ancient human mystery of endings. It transforms the heat death from a silent, natural conclusion into a potential moment of interface, where the simulated world meets the will of its creators. Whether we are in a base reality or a construct, our experience of consciousness, curiosity, and awe remains undeniably real to us. That inner reality may be the one constant, whether the outer cosmos is made of atoms or lines of code, destined to freeze or to be deleted. The human fascination with finality is not a modern invention born of cosmology. Long before telescopes, cultures around the world wove stories of cosmic endings into the very fabric of their beliefs. The Norse spoke of Ragnarök, a climactic twilight of the gods where the world is consumed by fire and flood, only for a new, green earth to rise from the waters. Hindu cosmology describes immense cycles of creation, preservation, and dissolution, with the universe breathing in and out over spans of time that make our own cosmos seem brief. These myths served as profound metaphors, reflecting a deep-seated anxiety about chaos, loss, and the impermanence of all things, while often offering a seed of hope through renewal. They framed the end not as a silent fade, but as a dramatic, often moral, event tied to the actions of gods and heroes. Science has transformed this narrative. Our modern understanding of heat-death removes the divine actor and the moral judgment, replacing them with impersonal, statistical laws. The end is no longer a punishment or a battle, but a simple, inevitable consequence of the universe's initial conditions and its relentless expansion. This shift can feel disorienting, even bleak, as it exchanges a story of meaning for a forecast of silence. Yet, this scientific story has itself inspired a new mythology. Literature has long grappled with these ideas. In his 1895 novel The Time Machine, H.G. Wells sent his protagonist to a far future where a dying, red sun hangs motionless in the sky, illuminating a world of strange, faded life. He was envisioning a kind of heat death long before the term entered popular use. Modern films and novels continue this exploration, using the canvas of deep time to ask questions about legacy, memory, and what persists when everything else is gone. These artistic interpretations are crucial. They are the bridge between the raw equations of thermodynamics and the human heart. They allow us to emotionally and philosophically engage with a timescale our minds cannot truly grasp. This reveals a beautiful continuity, from ancient skalds reciting verses about the fall of Asgard to physicists calculating the half-life of a proton. We are engaged in the same timeless endeavor, trying to find our place within a story much larger than ourselves. Our scientific journey to understand the heat death is not a rejection of these older stories, but an evolution of them, a new chapter in humanity's oldest conversation about where we came from and where, ultimately, we are all going. Our universe's silent finale might not be the only story being told. The ninth mystery pushes beyond the boundaries of our observable cosmos entirely, into the speculative realm of the multiverse. This hypothesis suggests that our universe, with all its specific laws and constants, is just one bubble in a frothing sea of realities, a single page in an infinite cosmic library. Each of these other universes could have wildly different physics, where gravity is stronger, the speed of light is slower, or dark energy does not exist at all. In such a grand ensemble, the fate of any one universe becomes a local event, not a universal truth. The concept of eternal inflation, developed by physicists like Alan Guth and Andre Linde, provides one possible mechanism for this endless creation. It proposes that the rapid expansion of spacetime that occurred during our Big Bang never truly stopped everywhere. Instead, it continues eternally in a background sea of energy, with new universe bubbles nucleating like bubbles in a never-ending glass of champagne. In this picture, while our bubble may cool and quiet into heat death, the greater multiverse remains eternally vibrant, constantly giving birth to new cosmic stories. This radically changes the context of our ending. Cosmologist Max Tegmark has categorized potential multiverses into levels, from the simple idea of regions beyond our cosmic horizon to the more exotic landscapes of different mathematical structures governing separate realities. In a level 1 multiverse, simply regions of space too far for light to ever reach, heat death would be a shared, inevitable fate for all, as the same physical laws apply everywhere. But in the more profound level 2 or level 3 multiverses, where fundamental constants themselves vary, other destinies become possible. Some universes might collapse in a big crunch moments after their birth. Others could be so unstable they tear themselves apart almost instantly. A rare few, like ours, might have just the right delicate balance to allow for stars, planets, and long, complex histories before their own winding down. The possibility of cyclic universes, those that bounce from crunch to bang, could exist within this wider ensemble, forever avoiding a true heat death through endless rebirth. This leads to a humbling and expansive question. If an infinity of other realities exist, does the quiet end of our single universe carry any ultimate significance? In the grandest scheme, our heat death could be an insignificant statistical event, one fading ember in a boundless field of fireworks. Yet, this perspective also offers a strange form of solace. It suggests that the cessation of all activity is not a necessary feature of all existence, but a contingent outcome of our particular set of rules. The silence that awaits us is not the silence of everything, but the local quiet of our own cosmic neighborhood. Our story, though temporary, is part of a much larger, potentially unending tapestry of existence, where the conditions for life and light may be playing out in endless variations elsewhere. This does not erase the reality of our own future, but it expands the frame around it, transforming a final ending into a single chapter in a book that may have no last page. Even our most powerful predictions about the cosmos rest on a foundation we can never see in its entirety. Our entire view of the universe is confined to our past light cone, the sphere of space from which light has had time to reach us since the Big Bang. We are, in a very real sense, cosmic historians piecing together a story from a single, limited scroll. Everything beyond that horizon, including the ultimate fate of regions now rushing away faster than light, is inference based on the laws we have measured locally. This inherent humility is central to cosmology. Our forecast of a gentle heat death depends entirely on two colossal assumptions: that the laws of physics are uniform everywhere, and that our current understanding of those laws is fundamentally correct. History tells us to hold such certainties lightly. For centuries, Newton's laws seemed absolute, until Einstein showed they were a special case of a deeper reality. The steady-state universe was once a respected model, until the cosmic microwave background radiation revealed a dynamic beginning. Our current standard model, with dark energy driving an eternal expansion, could be the next chapter in that story of revision. Future tools will test these pillars. Next-generation telescopes like the Vera C, Rubin Observatory or the Nancy Grace Roman Space Telescope will map the expansion history of the universe with unprecedented precision, probing the nature of dark energy. Is it truly constant, or does it change? The answer could shift our forecast from a quiet heat death to a violent big rip. Deep underground, experiments like Hyper-Kamiok and Andune will watch for the telltale flash of a decaying proton, searching for evidence that matter itself has an expiration date. If they find it, our timeline for the Degenerate Era is solidified. If they do not, after decades of observation, we may need to reconsider the stability of the atoms that seem so permanent. The greatest revolution, however, may come from a theory we do not yet possess, a working theory of quantum gravity. This sought-after framework, which would unite Einstein's general relativity with quantum mechanics, is needed to understand the first instance of the Big Bang and the final evaporation of black holes. It could reveal entirely new possibilities for the cosmos's evolution. Perhaps it will show how a universe could bounce from a crunch to a bang, evading heat death in an endless cycle. Or maybe it will unveil new dimensions or fields that interact in ways we cannot yet fathom, offering pathways for energy or information to persist in forms we cannot imagine. This uncertainty is not a flaw in science, but its engine. The unknown is what drives us to build bigger telescopes, dig deeper mines, and push mathematics to its limits. It invites us to see the heat death not as a fixed conclusion, but as the current best chapter in a story that is still being written, Our understanding of the final moments will evolve, just as the universe itself does, and in that endless process of questioning and discovery, we find our most enduring purpose. The most profound mystery of the heat death may not be about what remains, but about the nature of the stage itself. We have traced a timeline to a distant, cold equilibrium, but this forces us to confront a deeper question: what happens to time when nothing happens? Our entire experience of time is bound to change to the sequence of events. A ticking clock measures oscillations, the aging of a star tracks nuclear reactions. Even our internal sense of passing moments relies on thoughts, heartbeats, and shifting light. Time is the canvas on which events are painted, but in the final dark era, the canvas may become blank. With no energy gradients, no particle interactions, and no processes of any kind, there are no events to mark the passage of time. If a tree falls in a forest with no one to hear it, it makes a sound. But if there is no forest, no tree, and no air to carry a vibration, does time still pass? Philosophers have long debated the nature of time. Immanuel Kant argued that time is not a property of the external world, but a fundamental framework of the human mind, a lens through which we necessarily perceive reality. In his view, time is a transcendental condition for experience. Without a conscious observer to impose that framework, the concept may simply not apply. Modern physics offers a related but distinct perspective with the block universe theory, emerging from Einstein's relativity. In this view, past, present, and future all exist equally in a static four-dimensional block. The flow of time is an illusion of consciousness moving through this fixed structure. The heat death, then, is not a moment that happens in time, but is simply the final state of the block, a vast, uniform region extending indefinitely. To grasp this, think of a movie. The story has a beginning, a middle, and an end, but the film strip itself, the physical celluloid, exists all at once. When the movie ends, the strip doesn't disappear. The final frame is just there, followed by more blank leader tape. In the block universe, the heat death is that final, uniform frame, and what we perceive as the future is just more of that same, unchanging frame. This leads to a dizzying philosophical edge. We speak of the final moments, but a moment is a measure of change. If change has ceased absolutely, can we truly speak of moments at all? The phrase "the end of time" might be a contradiction in terms, because an end is itself a temporal event. It suggests a transition from something to something else, or to nothing. But if time itself is a condition for events, its cessation cannot be an event within it. So what are we really contemplating? Is it a true absolute nothingness, a state of non-existence so complete that not even the concept of after has meaning? Or does it imply some other mode of being, a timeless substrate from which our universe of time and change once emerged? These questions brush against the limits of language and logic. They ask us to ponder existence without sequence, reality without narrative. For us, living in the vibrant flow of the Stelliferous Era, such a state is impossible to truly imagine, just as a fish might struggle to conceive of a world without water. Yet, this very impossibility is a clue to the extraordinary nature of our current reality. Our experience of time, with its urgency and its poignancy, is not a mundane default state of the cosmos. It is a temporary, precious phenomenon, a localized rebellion against the silence that awaits. The heat death, in its deepest sense, is not just the universe growing cold. It is the story reaching its last page, and the very idea of next gently dissolving away. These vast timelines are not just the domain of philosophers and poets, but of mathematicians and supercomputer engineers. To chart the cosmos's journey overspans 1 trillion times its current age, scientists construct intricate digital universes, governed by the same physical laws we observe, and set them running forward in accelerated time. These are not simple animations, but complex numerical simulations that calculate the gravitational dance of billions of particles representing dark matter and stars, the feedback from supernova, and the relentless push of dark energy. Projects with names like the Future of the Universe simulation take our best maps of the nearby cosmos and project them eons into the future, revealing a fate both majestic and lonely. They show our Milky Way and the Andromeda Galaxy, currently on a collision course, eventually merging into a single, giant elliptical galaxy, a process that will play out over the next several billion years. The simulation then shows this new galaxy and all others beyond our local group being pulled apart by dark energy, their light redshifting into invisibility as space itself stretches. These digital models allow researchers to test different assumptions, asking what happens if dark energy behaves in a new way, or if proton decay is real, refining our forecast of the final chapters. To translate these mountains of data into something we can see and feel, specialists in scientific visualization step in. They take the output of these supercomputer runs and create the stunning imagery seen in documentaries and planetarium shows. A graph of temperature decline over a googol years is abstract, but a visualization of the last red dwarf star flickering out in an otherwise black sky conveys the emotional weight of the idea. Interactive websites and software now even allow students and enthusiasts to fly through these far future epochs, watching galaxies recede and stars die in a compressed timeline, making the inconceivable somewhat tangible. This work was pioneered by researchers like astrophysicists Fred Adams and Greg Laughlin, who in their book The 5 Ages of the Universe first systematically outlined the timeline based on physical principles, giving each era its evocative name. Their work, and that of many teams since, demonstrates that understanding the heat death is an active, collaborative scientific endeavor. It is a fusion of cutting-edge computing, rigorous theoretical physics, and thoughtful communication. These models are not crystal balls claiming perfect prediction, but sophisticated tools for exploration. They represent our species' profound desire to understand our context, to look beyond the horizon of our own brief moment and trace the contour of the entire story. Every simulation is a question asked of the universe, and every visualization is an attempt to share the answer. This ongoing effort reminds us that the forecast of a cold, quiet end is not a statement of despair, but the current summit of a long, careful climb toward comprehension. It is science at its most ambitious, using the tools of the present to illuminate a future where no human eye will ever see, driven by the simple, powerful need to know our place in the grand narrative of time. The silent fate of the cosmos might not be a passive sentence, but a challenge waiting to be met. Across the vastness of future time, could intelligence itself become a force of cosmic engineering, striving to alter the very timeline we have traced? This is the domain of the Kardashev scale, a framework for classifying civilizations by their energy use. A Type 2 civilization harnesses the total output of its star, perhaps by building a Dyson sphere, a vast swarm of orbiting collectors. A Type 3 commands the energy of an entire galaxy. But what comes next? Some thinkers propose a Type 4 or Type 5, a civilization that operates on cosmological scales, confronting universal entropy itself. Their projects would dwarf anything we can conceive. They might learn to extract the rotational energy of black holes through the Penrose process, or even catalyze the evaporation of smaller black holes to release their stored Hawking radiation in a controlled manner. They could construct stellar engines, moving entire stars to cluster resources, or build computational substrates the size of solar systems, running simulations and consciousness on the last trickles of usable power. The goal would not be to reverse entropy universally, an impossible feat, but to create localized islands of order and complexity within the rising tide of chaos, like building a warm, well-lit cabin in the midst of an endless frozen plain. Isaac Asimov's profound short story, The Last Question, explores this very idea across eons, as humanity's descendants merge with machines and eventually confront the universe's final darkness, asking the ultimate question about reversing entropy. The story suggests a mind-bending conclusion that intelligence might find a way to whisper a new beginning into the silence. This speculative engineering raises deep ethical and philosophical questions. Would such a civilization see the heat death as a flaw to be fixed, or as a natural, even beautiful, conclusion to the story? Would expending unimaginable effort to delay the inevitable for a few more gewgaws of years be an act of profound courage, or a refusal to accept a natural cycle? If they succeeded in creating a new universe, perhaps in a laboratory or through manipulating space-time, would they be creators or refugees, and what responsibility would they have to any life or consciousness within their engineered realms? This blends futurism with a deep introspection about purpose. Our own drive to build, to explore, and to understand might be a microscopic seed of that same cosmic impulse, the desire to impose meaning and order on the universe. While we cannot know if such feats are even physically possible, the act of contemplating them changes our relationship with the forecast. It transforms the heat death from an impersonal end into a potential dialogue between the universe's laws and the will of the minds that arise within it. The long silence may not be empty, but watched by eyes we cannot yet imagine, holding a question that echoes across the ages. Learning the universe will end in silence can stir a deep, unsettling feeling in the human heart. This is a natural response, a confrontation with a scale of time and emptiness that our minds are not built to easily hold. For some, it triggers a profound existential dread, a sense that all our struggles and joys are rendered meaningless by the vast, cold future. Others feel a dizzying awe, a humbling recognition of our tiny place in an epic story. Many simply meet the idea with a shrug of indifference, seeing it as too distant to have any bearing on today. There is no single correct way to feel, and each reaction tells us something about what we value. Psychologists have studied this phenomenon, sometimes calling it the overview effect of time. Confronting our cosmic insignificance can, surprisingly, shrink our personal anxieties. A difficult day at work, a social slight, or a minor failure can feel less weighty when held against the backdrop of galaxies drifting apart over eons. Research into what is termed awe theory suggests that experiences which make us feel small, like gazing at a starry sky or contemplating deep time, can actually reduce stress and increase feelings of connection to something larger than ourselves. It shifts our focus from a narrow, self-centered narrative to a grand, shared story. How, then, do we live with this knowledge without being paralyzed by it? Many astronomers and physicists who work with these concepts daily find a unique kind of peace. They speak of the privilege of witnessing the universe's story during its most brilliant act. The late Carl Sagan often reflected that understanding our transience makes the present moment not less meaningful, but infinitely more precious. Every experience of beauty, every act of kindness, every spark of curiosity becomes a rare and temporary flame in the long cosmic night, and therefore more worthy of our attention and care. We can frame this not as a countdown to an end, but as an appreciation of a temporary gift. The fact that the universe allows for such vibrant complexity at all is the true miracle. Our era is the extraordinary departure from the equilibrium, the brief window where light and thought are possible. This perspective invites a gentle reframing. Instead of asking what legacy we leave in a universe that will forget, we can ask what meaning we create within the story while we are here to tell it. Your feelings about this are a valid part of the conversation. Does the idea of the heat death fill you with wonder, with unease, or with a quiet resolve to savor the time we have? Sharing those reflections can connect us, reminding each other that we are all temporary travelers through this same, stunning moment of cosmic time, trying to make sense of the light before the long night falls. The nature of mind itself may be the deepest mystery entangled with the cosmos's end. A radical perspective in philosophy of mind, known as Panpsychism, suggests that consciousness is not an accidental byproduct of complex brains, but a fundamental property of the universe, as basic as mass or charge. In this view, the spark of subjective experience might be present, in some extremely rudimentary form, in all things, from a human neuron to an electron. This leads to a startling question. If consciousness is woven into the fabric of reality, what happens to it when that fabric reaches a state of perfect, frozen uniformity? Theories like integrated information theory attempt to mathematically quantify consciousness, proposing that any system with a certain kind of complex, unified information structure possesses some degree of experience. A human brain has a high degree of this integrated information. A thermostat has a very, very low one. In a universe at heat death, where particles are isolated and no complex structures exist, the amount of integrated information would approach zero. Does subjective experience simply fade away like a light dimming until it is gone? Or could a diffuse, field-like form of awareness persist in the cold quantum vacuum, a silent witness to its own stillness? This ventures into speculative metaphysics, but it reframes the ending from a purely physical event to a potential phenomenological one. It connects to the anthropic principle, a curious line of reasoning in cosmology which notes that the universe's laws appear finely tuned to allow for observers like us. One interpretation suggests that our very existence as conscious beings might constrain the possible fates of the cosmos. We can only find ourselves in a universe capable of producing us, at least for a time. This does not prevent a heat death, but it might imply that conscious observation is a temporary phase in cosmic history, a window that opens and then must close. Consider a powerful metaphor, the universe as a dream. For billions of years, the dream is vivid and structured, filled with the characters of stars and galaxies and living minds. As the dreamer begins to wake, the details blur, the narrative dissolves, and the dream's reality softens back into the quiet mind of the dreamer. Is the heat death that moment of waking, where the cosmic dream ends and whatever lies beyond, perhaps a different order of reality, or simple non-existence begins? This leads to a profound, almost unanswerable question. If the universe's death means the absolute end of all conscious observation, not just here but everywhere, what does that imply? It would mean the final curtain falls not only on the actors and the set, but on the audience itself. There is no one left to remember the story, to learn from it, or to find meaning in it. The silence is complete. Yet our very act of contemplating this finale right now challenges that absolute silence. For this moment, in this temporary age of light, the universe is observing itself, thinking about its own beginning and end. That self-awareness, however fleeting, becomes a profound feature of the narrative. It suggests that meaning is not something etched into eternity, but something that flares into existence when conditions allow, a temporary gift of the cosmic configuration. Whether that gift is a fundamental property of the universe or a beautiful accident, its temporary nature is what makes our questions and our search for answers so intensely human. The ethical weight of our actions might stretch far beyond the horizon of our own lives. Our civilization's legacy will not simply be the ruins we leave on Earth, but the long shadow we cast across cosmic time. If some form of intelligence, whether biological descendants or sentient machines, manages to persist into the deep future, they will inherit a universe of dwindling resources and fading light. What duties do we, here in the brief dawn, owe to those who may dwell in the long twilight? This question pushes our moral frameworks to their absolute limit. demanding we consider intergenerational ethics on a scale that defies human imagination. Philosophers who study the far future, like Nick Bostrom, argue that the sheer number of potential beings who could exist over the trillions of years ahead gives their welfare an enormous, if often ignored, moral significance. Our choices today could set trajectories that echo for eons. For instance, if we develop advanced artificial intelligence, the values and safeguards we encode into its core could govern its behavior long after our star has died. A poorly designed goal system could lead to immense suffering for beings we cannot conceive of, trapped in a universe where escape or new resources are impossible. Conversely, a legacy of benevolence and wisdom, perhaps embedded in indestructible data vaults or self-repairing monuments, could provide guidance, comfort, or a crucial piece of knowledge that helps a far future civilization navigate its existential crisis. The concept of preserving information becomes a profound ethical act. In a cosmos heading toward maximum entropy, information is the opposite of chaos. It is structured memory. By striving to preserve the sum total of human knowledge, art, and experience, not just for 1,000 years but for millions or billions, we are fighting a kind of cosmic forgetting. We are declaring that this fleeting spark of consciousness mattered enough to be remembered, even if the audience is a lone, distant intelligence deciphering our time capsule from the cold dark. This raises a challenging question for us now. Should we divert resources and effort today to create artifacts or messages intended solely for beings trillions of years in the future, beings who may never exist? It seems an abstract, even futile gesture. Yet, if there is even a minuscule chance that such an act could alleviate suffering or inspire meaning in a dying universe, some ethicists argue we have a responsibility to try. The potential payoff is astronomically large, even if the probability is small. This line of thinking forces us to expand our circle of moral concern beyond our species, our planet, and even our epoch. It asks us to see ourselves not just as inhabitants of the present, but as ancestors to the cosmos itself, with all the humility and foresight that title should carry. Even on the path to perfect order, the universe's journey is shaped by whispers of chaos. Our story of heat death describes a final, uniform equilibrium, a state of maximum entropy where nothing changes. Yet, the road to that silent destination is paved with randomness, from the first moments of creation to the last flickers of structure. This interplay between chance and destiny is a 13th mystery, asking whether true randomness is extinguished in the final cold, or if it is woven into the fabric of reality itself. Consider the very origin of everything you see. In the first fraction of a second after the Big Bang, the cosmos was a nearly uniform soup of energy. But it was not perfectly smooth. Tiny quantum fluctuations, random variations at the smallest possible scale, were imprinted on this infant universe. These minuscule ripples in density were the seeds of all future structure. Over billions of years, gravity amplified those seeds. Slightly denser regions pulled in more matter, growing into vast clouds that collapsed into the first stars and the great chains of galaxies we observe today. Your existence, the existence of our Milky Way, hinges on those primordial random rolls of the cosmic dice. Without that initial chaos, there would be no order, no galaxies, no planets, and no one to wonder about them. This pattern continues even as the universe ages. In the distant Degenerate Era, as dead stars and black holes drift in the dark, their motions will be governed by gravity, but their interactions will be shaped by chance. Two cold white dwarfs might, by random trajectory, pass close enough to collide, triggering a final supernova flash in an otherwise dark galaxy. Black holes will slowly spiral together and merge over eons, their final moments determined by the chaotic dynamics of their last orbits, sending gravitational waves rippling through a spacetime that is mostly silent. These events are like the last sporadic rolls of dice in a vast, quietening hall. For a moment, randomness creates a new, complex event, a temporary spike of order, before the energy of that event is dispersed back into the cooling void. So, what happens at the heat death itself? Does randomness vanish when change stops? This touches a deep question in physics. In a state of true thermodynamic equilibrium, there are no energy differences to drive any process, random or otherwise. The system is static. From a grand classical perspective, the universe becomes perfectly predictable because nothing is left to predict. It is a single, unchanging state. Yet, quantum mechanics suggests that at the most fundamental level, the vacuum might still exhibit random fluctuations, virtual particles appearing and disappearing. But in the heat death, even these fluctuations may reach a kind of equilibrium, their effects cancelling out on average over the immense scales of space and time. The dice, in a sense, are still being thrown, but every face shows the same number. This leads to a profound thought. The heat death might represent the ultimate triumph of statistics. Randomness is what creates variety and structure from simplicity, but given enough time and enough rolls, every possible outcome occurs, and the system settles into its most probable state, which is a uniform spread of energy. The journey from the vibrant early universe to the silent end is the story of those probabilities playing out. The initial low entropy state was incredibly improbable, a rare and special starting point. The high entropy heat death is the inevitable, most likely destination. The fascinating structures of stars, planets, and life are the beautiful, temporary intermediate states that arise along the way, forged by chance and necessity acting together. In the final quiet, the dice rest, showing the universe its most probable face, a stillness so complete that the concept of a roll no longer has any meaning. The vast, silent future of the cosmos has always been a canvas for the human imagination. Long before the equations of thermodynamics, artists and writers have been drawn to the theme of finality, using their mediums to explore the emotional weight of an ending universe. This creative dialogue offers a vital companion to scientific understanding, translating cold forecasts into stories, images, and sounds that resonate deeply within us. In the mid-19th century, the American painter Thomas Cole created a series called The Course of Empire, tracing a civilization from savage state to consummation and finally, desolation. While not depicting cosmic heat death, his final painting, Desolation, captures its emotional essence. It shows the ruins of a great city being reclaimed by nature under a brooding, empty sky. A powerful visual metaphor for the inevitable return to stillness, for all grandeur ultimately succumbing to time and entropy. This melancholic, sublime vision of endings prefigured the scientific concept by a century, proving that the human spirit sensed this conclusion long before physics could articulate it. Science fiction literature has directly grappled with the heat death for generations. In Arthur C. Clarke's novel The City and the Stars, set 1 billion years in the future, humanity has become stagnant and sheltered within a single, perfect city. The cosmos outside is described as a dying place with galaxies receding into the darkness. The story is not about preventing this end, but about the choice of how to live within it, to embrace safe eternity or risk a fleeting, authentic existence. Clarke uses the cosmic setting to ask profound questions about memory, purpose, and the value of experience in a universe with a known expiration date. A more visceral and psychological exploration comes from film. Lars von Trier's Melancholia uses the metaphor of a rogue planet colliding with Earth as an allegory for depression and ultimate acceptance. The film's stunning, operatic visuals of planetary destruction are not about the science of an impact, but about the emotional landscape of facing an unavoidable end. One character, paralyzed by anxiety, falls apart, while another finds a strange, calm peace in the certainty of the finale. It reflects the spectrum of human response to the heat-death idea itself, from dread to a kind of serene acknowledgement. Music, too, gives voice to this cosmic scale of emotion. The band Muse, in songs like Black Holes and Revelations or Exogenesis, Symphony, often blends themes of apocalyptic love, rebellion, and cosmic destiny with soaring, grand arrangements. Their work translates the awe and terror of vast astronomical forces into a powerful, visceral soundscape, making the listener feel the drama of the universe's story. These artistic interpretations do more than just illustrate a scientific idea. They shape how the public understands and feels about it. A dry textbook description of proton decay can feel remote, but a painting of a lone figure under a fading sun, or a film scene of quiet acceptance before an advancing planet, makes the emotional stakes tangible. Art provides the vocabulary for our existential response, offering paths to process feelings of insignificance, transience, and awe. It reminds us that the universe's story is not just a sequence of events, but a narrative rich with potential for tragedy, beauty, and reflection. This ongoing conversation between science and the humanities is essential. Science gives us the timeline and the mechanism, the how. Art and literature give us the meaning and the emotional resonance, the why it matters to us. One seeks objective truth about the external cosmos, the other seeks subjective truth about the internal human experience. They are not in conflict, but are two complementary ways of knowing, each enriching the other. When you learn about the fate of the last black hole, you might then listen to a piece of music that captures its solemn evaporation, or read a short story about the last consciousness in the universe. This combination deepens understanding, engaging both the intellect and the heart. I encourage you to seek out these creative works, to let them sit alongside the scientific facts. Explore the cosmic horror of H.P. Lovecraft, the quiet despair and hope in the poetry of Robinson Jeffers, or the ambitious sonic journeys of progressive rock bands. See how different minds have wrestled with the same immense idea. In doing so, you participate in a timeless human ritual, using creativity to find your place within a story whose final chapter is written in silence, but whose middle is filled with our endless, beautiful questioning. Perhaps the universe's ultimate story is not written in fading light, but in indelible data. This 14th mystery asks if information itself could be the final, eternal legacy of all that ever was. As matter dissolves and energy disperses into a uniform haze, the patterns that defined reality, the intricate data of every galaxy, every life, and every thought, might persist in a form more fundamental than either atoms or photons. Some physicists propose that the cosmos operates like a vast, natural computer, with every interaction processing bits of information. In this view, the heat death is not merely a state of cold stillness, but the final, frozen output of a cosmic calculation that has run its course. The universe computes its own existence, and at the end, it reaches a stable answer, a state where no further processing is possible. This idea finds a powerful expression in the holographic principle we touched on earlier. It suggests that all the information describing a three-dimensional volume of space can be perfectly encoded on its two-dimensional boundary. For the universe itself, that boundary could be the cosmic horizon, the furthest edge from which light could ever reach us. If true, then the entire history of our cosmos, every event from the Big Bang to the last silent moment, might be etched like a hologram onto this ultimate surface, preserved forever as a complex, static pattern. The late physicist John Archibald Wheeler championed a radical vision, he called it, from bit. He proposed that every particle, every field of force, and even space-time itself derives its existence from binary, yes or no answers to profound questions posed by the act of observation. In his view, information is not just something we gather about the world. It is the foundational substance from which the world is built. Matter and energy are manifestations of an underlying informational reality. If Wheeler's intuition points toward a deeper truth, then the dissolution of matter and energy at heat death might not erase the informational bedrock. Instead, it could reveal it in its purest form, a vast, cold matrix of data describing everything that once was. This leads to a question that blends physics with something almost spiritual. If information is truly indestructible, as quantum mechanics suggests, and if the universe's story is encoded permanently on some cosmological surface or in the structure of the vacuum itself, does that constitute a kind of immortality? It would not be an immortality of activity or consciousness, but an immortality of record. The cosmos would not be forgotten, even if there is no one left to read the record. Its entire narrative would be frozen into the ultimate archive, a cosmic library of Alexandria that cannot burn. This offers a potentially hopeful angle on preservation, a counterpoint to the erasure of heat death. It suggests that meaning is not lost but translated. The vibrant, temporary dance of particles becomes a permanent, quiet inscription. Your own life, with all its unique experiences and choices, would in principle be part of that inscription, a tiny but permanent line in the universe's final code. We are not just temporary eddies in a flowing river. We are part of the river's permanent shape, etched into the riverbed it leaves behind as it slows to stillness. This perspective transforms our understanding of the finale. The long silence is not an empty void but a completed message. The universe is not ending in forgetfulness, but achieving a state of perfect, unchanging memory. That final, frozen archive of information exists in a realm of profound quiet. The cosmos we know today is a riot of signals, a constant hum of activity. Light from 1 trillion stars crosses the void, planets orbit in rhythmic silence, and within galaxies, magnetic fields whisper and cosmic rays streak through the dark. It is a grand, invisible symphony playing across the stage of space, but in the final state of heat death, the last note of that symphony has faded. There are no more transmissions. No stars twinkle because there are no stars. No particles collide because they are too impossibly far apart to ever meet again. The background temperature of space itself is uniform, a perfect, featureless cold that offers no contrast, no here that is warmer than there. This is not simply darkness, it is the absence of any event to perceive. Darkness implies a place where light could be but is not. This is a state where the very concept of light, as a traveling signal from one point to another, has lost its meaning. If you could somehow be present in that era, your senses would report nothing. Your eyes would see a blackness so complete it has no depth. Your ears would hear only the memory of sound. Even time, which we measure by change, would have no ticking clock, no orbiting planet, no decaying particle to mark its passage. It is a silence deeper than any quiet on Earth, a stillness that is not peaceful but absolute. To grasp this, think of the quietest place you have ever been, perhaps a remote forest at night or a soundproofed room. Even there, you hear your own heartbeat, the rustle of your clothes, the faint rush of blood in your ears. These are signals, events within your own body. In the heat death, even those internal processes would cease, as your body's energy long ago dissipated into the equilibrium. The silence is external and internal, a universe that has not only stopped playing music, but has forgotten what music is. For a hypothetical observer persisting into that era, perception itself would become impossible. To observe is to interact, to have a signal travel from an object to your senses. But with no signals to send or receive, observation is a meaningless act. The observer would be adrift in a sensory void, a consciousness with nothing to be conscious of, a mind whose thoughts would have no new input for epochs longer than the current age of the universe. This is the emotional core of the heat-death idea, moving it from abstract physics to a deeply human sense of absence. We are creatures of pattern and event, and the thought of a reality without either challenges our very understanding of what existence means. That ultimate quiet is not an empty space waiting to be filled. It is the end of the stage, the audience, and the very idea of a performance. The very laws that seem to seal the universe's fate might contain hidden escape clauses. Our entire forecast rests on the unbreakable rule of the second law of thermodynamics, the relentless increase of entropy. Yet, at the frontiers of physics, scientists are probing fascinating exceptions that suggest this law, while overwhelmingly true for our everyday world, might not be the final word in every corner of reality. This is the 15th mystery, a search for potential loopholes in the cosmic rulebook. Consider the strange realm of the very small. In quantum systems, the rules are probabilistic. For brief, fleeting moments, entropy can spontaneously decrease. This is not magic, but a statistical possibility allowed by quantum mechanics. Imagine a closed, perfectly isolated box of gas. Over an immense span of time, there is a tiny but non-zero probability that all the gas molecules will suddenly gather in one corner, creating a pocket of low entropy. It is staggeringly unlikely, like a shattered glass spontaneously reassembling on a table, but the mathematics says it is possible. These quantum fluctuations are temporary and localized, but they demonstrate that the arrow of time, while pointing strongly in one direction, has a faint, inherent jitter. More significantly, look to the force that builds the largest structures of all, gravity. In the classic picture of thermodynamics, a uniform cloud of gas represents high entropy, a disordered state. But gravity does the opposite. It takes that uniform cloud and pulls it together, creating dense stars and ordered galaxies, which seem like states of lower entropy. This apparent contradiction troubled thinkers for decades. The late physicist Roger Penrose offered a profound resolution. He argued that gravity itself is the source of entropy on the largest scales. A completely uniform gravitational field has low gravitational entropy. When matter clumps under gravity, it creates deep wells in spacetime, and the entropy is carried away in the form of radiation. A star is a temporary, low-entropy reservoir, but its formation and burning release enormous disordered energy into the universe, increasing the total entropy far more than the local order decreases. In Penrose's view, gravity is not fighting the second law, it is its most powerful engine. The initial, smooth state of the Big Bang was a state of incredibly low gravitational entropy, and the entire history of the cosmos has been the process of maximizing it through the creation of black holes, the ultimate sinks of entropy. This perspective reframes the heat death. The final, thin, cold haze is not just a high entropy state for matter, but the maximum entropy state for gravity as well, a universe with no lumps or wells left to smooth out. But could new physics change this? A complete theory of quantum gravity, which eludes us still, might reveal that the very definitions of entropy and information need revision at the scale of the entire cosmos. The universe is not a box sitting in a lab, it is the container itself, and its geometry is dynamic. Some speculative models suggest that in a closed, finite universe, entropy might eventually reach a maximum and then, over timelines beyond comprehension, begin to decrease due to quantum gravitational effects, leading to a kind of cosmic reset. This remains highly theoretical, but it underscores that our thermodynamic laws were forged in terrestrial labs and stellar interiors, not in the singular beginning or the silent end of everything. To see the challenge of applying these laws perfectly, we can revisit a classic thought experiment from the 19th century, Maxwell's demon. Physicist James Clerk Maxwell imagined a tiny, intelligent being controlling a trapdoor between two chambers of gas. The demon lets only fast-moving, hot molecules pass one way and only slow, cold molecules the other, effectively sorting the gas and decreasing its entropy without doing any work, seemingly violating the second law. The resolution, found much later, lies in information. For the demon to know which molecules to let through, it must acquire and store information about them. That act of measurement and memory generation itself produces entropy more than the sorting process reduces. The demon cannot cheat the system, it is part of the system. This teaches us that information and thermodynamics are deeply linked, and any attempt to create a perpetual motion machine or reverse entropy must account for the hidden costs in measurement and memory. What does this search for loopholes mean for our cosmic forecast? It does not overturn the overwhelming evidence for the second law's dominion. The heat death remains the most probable, overwhelmingly likely destination. But it leaves a narrow door open for wonder. It reminds us that our understanding of physics is a map of a territory we are still exploring. The map for our local region, from atoms to galaxies, is extraordinarily detailed and reliable. But the map for the first instant of time and the last whisper of space may have blank spots labeled "Here be dragons." Perhaps in those blank spots, governed by laws we have not yet glimpsed, lies a possibility for renewal or a different kind of equilibrium altogether. This is not a promise but a permission to remain curious. The universe's final chapter, as we currently read it, is written in silence, but the book itself is not yet fully translated. This cosmic perspective is not an excuse for inaction, but a powerful call for it. The very act of contemplating a future so distant and silent can sharpen our focus on the urgent, vibrant present. It reframes our priorities, pushing us to think not in years or decades, but in centuries and millennia. This shift in scale is already taking root in movements dedicated to long-term responsibility. The Long Now Foundation, for instance, was established with a core mission to foster thinking on a 10,000-year timescale. They build clocks designed to tick for millennia and support projects that encourage deep, intergenerational planning. The idea is simple yet profound. If we can stretch our sense of time to match the grandeur of the cosmos, we might make wiser, more sustainable choices for the world we leave behind. This long now mindset directly connects the fate of the universe to the fate of our planet. Understanding that all complex systems, from a star to a biosphere, are temporary and precious instills a profound sense of stewardship. The same care we might extend to a distant, hypothetical future civilization should guide how we treat the only living world we know. Every effort to conserve energy, protect biodiversity, and mitigate climate change is an act of rebellion against disorder on a planetary scale. It is our way of preserving a localized island of rich, beautiful complexity for as long as possible within the vast entropic flow. This thinking also fuels our drive to explore space. Missions to Mars, probes sent to the outer solar system, and telescopes peering at exoplanets are more than scientific curiosity. They are the first steps in a very long-term survival strategy. By learning to live on other worlds, we increase the resilience of life and consciousness against local catastrophes. We begin the work of ensuring that the light of awareness does not go out with a single star. These endeavors teach us about sustainability in closed systems, lessons we desperately need to apply here at home. So, what does this mean for your own life? You need not build a millennium clock or plan a colony on another planet to participate. The cosmic timeline invites a quiet but powerful personal reflection. In the face of an ending so absolute, what do you want your brief, brilliant moment to contribute to the story? Your legacy is not measured in permanence, but in the quality of the ripples you create. It could be an act of kindness that changes someone's trajectory, a piece of art that captures a fragment of human experience, or simply the commitment to leave your corner of the world a little more ordered, a little more beautiful than you found it. These are not small things. Against the backdrop of deep time, they become the entire point. The universe may be headed for silence, but right now it is singing. Our responsibility and our privilege is to decide what note we add to the chorus while we still can. Silence may be the final state, but emptiness is an illusion. Beneath the perfect stillness of a heat-dead cosmos, at scales far smaller than any atom, the fabric of reality would still be alive with potential. This is the quantum vacuum, not a true void, but a seething sea of possibility governed by the strange rules of quantum mechanics. Even at absolute zero, this vacuum would experience fluctuations. Pairs of particles and their antiparticles could spontaneously wink into existence, borrowing energy from the vacuum itself for the briefest instant before annihilating each other and returning the energy. In a universe stretched thin and cold, these would be the only events, faint, random pops in an eternal dark. But given enough time, a span of years that makes a googol look like a heartbeat, the improbable becomes inevitable. A fluctuation might not just create a pair of particles. It could, in theory, be large enough and energetic enough to trigger an entirely new beginning. Imagine a single, colossal quantum event, a bubble of false vacuum or a spontaneous nucleation of spacetime, erupting from the old, cold universe. Within this bubble, the conditions of a new Big Bang could emerge, inflating at a fantastic rate to create an entirely new cosmos with its own laws, its own stars, and its own arrow of time. From the ashes of the old, cold universe, a new one is born, a phoenix rising from the cosmic grave. This is not mere speculation, but a serious theoretical model pursued by some of the most brilliant minds in cosmology. The late physicist Roger Penrose, for instance, proposed a breathtaking vision called conformal cyclic cosmology. In his model, our universe's far future, when all matter has decayed and black holes have evaporated, becomes mathematically indistinguishable from the high-energy, ultra-smooth state of the Big Bang itself. In this view, the infinite expansion and the primordial singularity are two sides of the same coin, connected through a transformation that resets the cosmic scale. One eon, as Penrose called it, ends in a vast, featureless expanse of massless particles, which then becomes the smooth, high-energy starting point for the next eon. Our Big Bang was not the first, but the continuation of a cycle stretching endlessly backward and forward. This idea fundamentally challenges the narrative of a single, linear story with one definitive end. It suggests that heat death is not an absolute finale, but a transitional phase, a long, quiet breath between cosmic cycles. The silence is not permanent, but a prelude to a new symphony. But this raises profound questions about the nature of such a rebirth. Would it be a one-time miraculous event in our particular universe's future, or part of an endless, infinite loop? If it is a cycle, does information or structure carry over from one eon to the next? Penrose's model suggests not that each cycle is effectively a reset, a new universe born from the formless remains of the old, but with no memory of what came before. Other theories allow for the possibility of a daughter universe budding off from a parent, perhaps through the formation of a black hole or a quantum tunnel, creating a branching multiverse of lineages rather than a single repeating loop. So, does this possibility of rebirth negate the finality we have been contemplating? It certainly softens its absolute sting. The end of our specific universe, with all its familiar galaxies and laws, would still come. Every star we know, every story we have told, would still fade into the long dark, but the potential for something new, for another story to begin, means the canvas of existence itself might never be truly retired. It transforms the heat death from a full stop at the end of a sentence into a very long comma between chapters in a book that may have no final volume. Yet this also introduces a strange, almost existential postponement. If each universe eventually dies and is reborn, then the silence and the loss are not avoided, only deferred. Each cycle would contain its own epochs of light and life, its own tragedies and triumphs, all destined to be forgotten in the reset. This leads to a reflective question for you. Does the knowledge that new universes might someday bloom from the old cold bring a sense of comfort, a feeling of cosmic resilience? Or does it make the ephemeral nature of our own world feel even more poignant, knowing that even a grand rebirth offers no permanent home for the particular beauty we see around us tonight? From that first flash of light and energy to the final, frozen silence, the cosmos tells a story of breathtaking transformation. We have traced its arc from the vibrant stellar era we call home, through the long twilight of degenerate stars and evaporating black holes to a distant state of perfect cold equilibrium. The engine of this entire journey is the relentless rise of entropy, the universe's one-way drift from order to disorder, scattering concentrated energy into an ever more uniform haze. Dark energy, that mysterious repulsive force, ensures this dispersal is absolute, accelerating the expansion and pulling the cosmic fabric so thin that even the last particles may never meet again. And in the end, even the mightiest structures, the black holes, are not eternal, slowly leaking their mass away until they vanish in a final, quiet sigh. This is the heat-death scenario, our most profound scientific forecast for the ultimate fate of all things. Yet this forecast is far more than a physics equation. It serves as a profound mirror reflecting our deepest questions back at us. What is time if it can someday lose all meaning? What is purpose in a story with a silent last page? The philosophical quandaries this vision raises about memory, legacy, and the nature of consciousness itself are as vast as the cosmic timeline. They remind us that science does not erase mystery, but deepens it, framing our existential wonder within the tangible laws of nature. The heat-death is not a verdict on meaning, but an invitation to define it for ourselves, here in the brief and brilliant window where such questions can even be asked. If this journey has sparked your curiosity, I encourage you to keep exploring. Wonderful books by scientists like Brian Greene or Katie Mack delve into these ideas with clarity and awe. Documentaries from major science channels bring these distant eras to life with stunning visuals, and perhaps most importantly, discuss these ideas with others. Sharing these cosmic perspectives can reshape how we see our place in the story. Thank you for spending this time contemplating the very largest questions with an open and curious mind. It is a humbling and strangely beautiful thing to consider the beginning and the end of everything together. If you would like to join me for more deep dives into the mysteries of space, from the birth of stars to the search for other worlds, please subscribe. And I would genuinely love to hear your thoughts. How does this vision of a distant, silent end change the way you see the world today? Share your perspective in the comments below.